Welcome to this problem solving session number 9. In this problem solving session, we will solve problems related to quantum harmonic oscillator interacting with a bath or environment. Now the first problem, consider a quantum harmonic oscillator described by the Hamiltonian h is equal to h0 plus v, where h0 is h cross omega a dagger a is the bare Hamiltonian. So I have not written plus half here, so because that's constant, and V is equal to QF, where F is a force exerted on the oscillator due to coupling to a bath consisting of another quantum system or an ensemble of such systems which commutes with the position Q cap, so that the linear forcing F, the dissipation rate is given by this expression. Okay, so to do this problem, you have to recall the Fermi golden rule, which we have discussed in details in the supplementary lecture. Also, I have even if you have missed the supplementary lecture or you have not gone through that, but you know the Fermi golden rule that we wrote in the lecture class. So the Fermi golden rule says that the transition rate for a system going from the state I to the state F is given by this expression, that is 1 by h cross square. You are going from the state I to the state F, and AS is the system operator, so this mod square, and the Fourier transform of the correlator, that is f of t. These are the bath operators. The system is interacting with the bath operator via this operator f, and this is the Fourier transformation. So this we know. In fact, also we know that this is nothing but the spectral noise density, or simply SFF at omega, where omega is equal to EI minus EF divided by H cross. Okay, or let me write it here as gamma Fi is equal to 1 by H cross square modulus of this matrix element, that is I to F, you are going via AS. Okay, and SFF evaluated at omega is equal to EI minus EF by H cross. So here, while I write this formula, omega is considered to be positive because this I, if you recall the lecture, we are going from the state higher energy state to the lower energy state. So this is the transition rate. Okay, now let us consider our quantum harmonic oscillator, and let's say we have energy levels like that. All of them are equally spaced. So this is, say, the state n, and this one is n plus 1. Then you have higher energy levels, and here it is, say, n minus 1. Okay, now the rate of transition for the system when it's going from the state, say, n to n plus 1, that is, the system is going in the upward direction, then the formula, if I apply, I will have 1 by h cross square modulus, you are going from n to n plus 1, and the system operator here is q cap, that is the position operator, then mod square, and SFF, as per our expression, will have omega is equal to En, because we are going from En to n plus 1. So this is what I have. So actually, because I am taking positive omega, so omega, as per my definition, I will take it positive. So En plus, here we are going from the upward direction, so going from the lower energy state to the higher energy state. So, and omega we are taking to be positive. So clearly I will write it simply as minus omega. So this would be minus omega. I hope you get the idea here. Now let me work out this quantity n plus 1 q cap n, and q cap is, you know, it is 0 point fluctuation. Okay, q cap is the 0 point fluctuation into a plus a dagger. So therefore I have here, it would be n plus 1 a plus a dagger n. So if you evaluate it, you can see that you will get x, you will have 0 point fluctuation, and this will give you n plus 1 square root of n plus 1. Okay, that is what you will get, because then you will have, you know, n plus 1, that will give you 1. But if you apply a on n, then you will get n minus 1. Because of the orthogonality, the other term will vanish. So you will simply, you will end up with this expression. Now you can write gamma n to n plus 1 is equal to x 0 point fluctuation square divided by h square n plus 1 spectral noise density evaluated at minus omega. Or I can write it as n plus 1 gamma up, where gamma up is the upward transition rate for a single photon. So that is, I will just write gamma up is equal to x 0 point fluctuation square SFF evaluated at minus omega. So this is one expression we have. Let me say this is my equation number 1. Similarly, you can work out the transition rate when you are going in the downward direction, n to n minus 1. That would be equal to 1 by h cross square. You have to evaluate this quantity. You are going from n to n minus 1 in the downward direction you are going. Q is the system operator, it's mod square. This time you will evaluate SFF at plus omega, right? Because you see that here omega is equal to en minus 1 by h cross, and harmonic oscillators are equally spaced, so this is a positive frequency, so therefore we have to write here plus omega. Okay, and similarly if you evaluate it, you will get it as x 0 point fluctuation square divided by h square n SFF at plus omega. Okay, or I can write it as n into gamma. Now we are going in the downward direction, gamma. So therefore we have another formula, n to n minus 1. Okay, now as per the definition, the dissipation rate is the downward transition minus the upward transition. For dissipation to happen, this quantity, the downward transition rate has to be higher than the upward transition rate. So now gamma down, this quantity, from here, as you can see, this is gamma up, and gamma down also you can read out from here very easily. So therefore if I put it, I will have here x 0 point fluctuation square by h square SFF at omega minus gamma up is x 0 point fluctuation square by h square evaluated at SFF evaluated at minus omega. So this implies that we get gamma is equal to x 0 point fluctuation square by h square SFF at omega minus SFF evaluated at minus omega. So this is the dissipation rate, and it's an important formula worth remembering. Now let us work out this problem. Express temperature T and the average number of phonons n of a quantum harmonic oscillator in terms of the spectral noise density function SFF omega. Okay, let us do it. Now please refer to lecture 28, the lecture class, where we obtain these expressions for spectral noise density as xi of omega, where xi is the Langevin noise. This was equal to twice m gamma m h cross omega. Gamma m is the dissipation rate of the mechanical oscillator, into n of omega, that is the average number of phonons or quanta of the harmonic oscillator. This was for when omega is greater than 0. And then we also got as xi at minus omega at the negative frequency, that is equal to twice m gamma m h cross omega n of omega, and this is for omega less than 0. Let's say this is formula number 2. Now here the Langevin noise operator xi takes the role of the Bath operator f, as explained in the previous problem. We have explained about this Bath operator in the previous problem. Now from equation 1 and 2 we can write, if I take the ratio of these two expressions, then you will see that instead of xi, now I will write f as ff of omega divided by sff at minus omega. That would be equal to n of omega plus 1 divided by n bar of omega. Okay, from here you can see I can write this as 1 plus 1 by n bar of omega, that is equal to sff omega divided by evaluated at minus omega. Okay, so from here I can write 1 by n of omega is equal to sff omega minus sff at minus omega divided by sff at minus omega. Okay, so from here I can work out the average number of phonons in terms of the spectral noise density function as sff evaluated at minus omega divided by sff at omega minus sff at minus omega. So this is what I obtain. Now regarding the temperature, you see we know that average number of phonon is given by this expression 1 divided by e to the power h cross omega by kBt minus 1. So from here I can write e to the power h cross omega by kBt is equal to 1 plus 1 by n bar, and which actually we have worked out. This expression I already worked out. So if I put it here, then I will get it as sff omega divided by sff at minus omega. Okay, and you can see now if I take the logarithm on both sides, then I will get h cross omega by kBt is equal to logarithm of sff omega divided by sff at minus omega. And from here I can write the expression for the temperature T very easily. That would be T is equal to h cross omega by kb. Kb is the Boltzmann's constant, logarithm of sff omega divided by SFF at minus omega to the power minus 1. Now let us work out this problem. The symmetrized power spectral density of an operator O cap is defined as this. This is the definition for symmetrized power spectral density. You are asked to show that the symmetrized force spectral density SFF omega for F cap, which is the fluctuating operator that we have discussed in problem number 1, is this. So this is what we are asked to find out. And also at very high temperature, that is when kBT is much greater than S cross omega, we have to show that this expression for the symmetrized force spectral density reduces to this expression. Okay, let us do it. So as per definition of the symmetrized power spectral density of an operator, for the operator F, the fluctuating operator F, this quantity is now defined as SFF at omega plus SFF at minus omega divided by 2. As you can see that this quantity SFF bar or the symmetrized power force spectral density, it quantifies the fluctuation introduced to the quantum harmonic oscillator from environment, and this fluctuation arises from the sum of power spectral density at positive frequency omega and at the negative frequency minus omega. And also you know that in the quantum regime, these two quantities which we have actually shown in the class, SFF omega is not equal to SFF at minus omega. In the quantum regime they are not equal, but in the classical regime they are equal. So these things we know. And also I told you that F plays the role of quantum Langevin noise here. Okay, these are already we know. Okay, now let us work out the expression. We know that the dissipation rate gamma for the mechanical oscillator, that is gamma m evaluated at frequency omega, this expression already we have worked out in the previous problem, that is x square 0 point fluctuation divided by h cross square SFF evaluated at omega minus SFF at minus omega. Okay, this is known to us, where this x 0 point fluctuation for the harmonic oscillator is s cross divided by twice m omega square root, and therefore I can write gamma m is equal to 1 by twice m h cross omega into SFF at omega minus SFF evaluated at minus omega. Okay, so from here I get SFF at omega minus SFF at minus omega is equal to twice m gamma m h cross omega. So this is one expression we have. Also from the previous problem we have worked out the average number of quanta in the harmonic oscillator in terms of the spectral noise density, that is SFF at minus omega divided by SFF at omega minus SFF at minus omega. Okay, from here I have this expression SFF at omega minus this quantity evaluated at minus omega. This is equal to 1 by n bar SFF evaluated at minus omega. Alright, now I have these two expressions at my disposal. This is say equation 1 and this is equation 2. I can play with these two, and from here I can, one thing I can immediately write is from these two expressions, one quantity that I can work out is SFF. Okay, because I know what is this expression from here. So using this, I have SFF at minus omega is equal to twice m h cross omega gamma n bar. So I know this quantity, so I have to find out the other quantity, that is SFF at plus omega. That would be equal to 1 plus 1 by n bar, and SFF at minus omega is known to me, so let me put the expression for that, twice m h cross omega gamma m n bar. Okay, from here I have SFF at omega is equal to I'll have n plus 1 into twice m gamma m h cross omega. So I now know the noise spectral density at plus omega as well as minus omega, so it is easy for me to work out this symmetrized function at frequency omega. That would be SFF omega plus SFF at minus omega by 2. If I put down the expressions, you can see that I will, okay, let me put it down. First one I have n bar plus 1 twice m gamma m h cross omega. The other one is twice m h cross omega gamma m n bar divided by 2, and from here I get SFF bar at omega is equal to m h cross omega gamma m 2n plus 1. So this is the required expression. Okay, now the other part is what happens at very high temperature. For that, to analyze that, we know that this average number of quanta n bar is equal to 1 by e to the power h cross omega by kBt minus 1. Now at very high temperature, that means when h cross omega is much less than kBt, for this we have this n bar is nearly equal to kBt divided by h cross omega, and therefore I can now write SFF at omega, this average or this symmetrized function would be equal to twice m gamma m h cross omega and then kBt by h cross omega. So what I will have here is twice gamma m kBt, okay, into m is also there. So this is what I have at very high temperature. That means when kBt is much greater than h cross omega. As you can see that this particular function is now independent of frequency, so we have that this spectral noise density is obviously frequency independent, so they are symmetric in frequency, and this is the case for when we are in the classical regime that we also discussed in the class. Let us now work out this problem. This is a simple problem where our goal is to explore various limits of the mechanical susceptibility. So as we have learned in our lecture classes, that the mechanical susceptibility of the mechanical harmonic oscillator was obtained as this, where chi m is the mechanical susceptibility, omega m is the resonance frequency of the oscillator, m is the mass, and gamma m is the dissipation rate. You are asked to show that the low frequency response of the oscillator is given by, low frequency means when the omega tends to 0, that susceptibility modulus of the susceptibility would be given by this, where K is the spring constant. K is equal to m omega m square. And you are asked to show that at high frequency, the response of the oscillator is given by this expression. And finally, you are asked to show that near resonance, the susceptibility for a high Q oscillator can be approximated by using this expression, which is a Lorentzian. So let us do it. It's a simple problem. Let me first of all write down the expression for chi m, the mechanical susceptibility, that is equal to 1 divided by m into omega m square minus omega square minus I gamma m omega. Okay, so this is what we have. The first part of the problem is very easy, because as you can see, as omega tends to 0, I can write chi m of omega is equal to 1 divided by m omega m square. These are the characteristic parameter of the oscillator, and 1 by m omega square is nothing but the spring constant K. Or if I talk about the modulus, and this actually I have in the limit omega tends to 0, so you have to be careful here. This, when I'm writing, we are writing it in the limit omega tends to 0. So modulus of the susceptibility is simply 1 by m into omega m square, and that is the spring constant. In fact, physically speaking, this result quantifies the response of a constant force, and therefore it is independent of friction, as you can see, as well as the mass, because K is the characteristic parameter of the system. Now going over to the second problem. In the high frequency limit, what happens? To do this, first of all, let me simplify this expression, because I have to work out the modulus. Okay, let me do it. Chi m of omega is equal to 1 divided by, I have m into omega m square minus omega square minus I gamma m omega. So if I want to find out the modulus, so first of all, let me find out chi m of omega mod square. That would be equal to 1 divided, it is easy to see, you have to take the multiplication of the complex conjugate, then you will get m square omega m square minus omega square whole square. Okay, and then you will have plus m square gamma m square omega square. So this is the expression you are going to get. Let me open it up. If I open it up, then I can have 1 divided by, let me take m square common, then I have omega m to the power 4 plus omega to the power 4 minus twice omega square omega m square plus gamma m square omega square. Now if I take omega to the power 4, let me take it outside. 1 divided by m square omega to the power 4, that would be 1 plus omega m to the power 4 by omega to the power 4, okay, minus twice omega m square by omega square plus gamma m square by omega square. So the modulus of the mechanical susceptibility at very high frequency, that is omega tends to infinity, that would be equal to 1 by m omega square, as these terms will vanish. In fact, this is nearly equal to 0. What it means is physically that the oscillator essentially behaves like a free particle, and the response of the oscillator is inertial and is independent of stiffness and damping. Now let us do the last part of the problem. In the last part, we are asked how the response function behaves at the resonance, that is omega is nearly equal to, say, omega m. Then this susceptibility expression chi m of omega, let me write it once again. This is 1 divided by m into omega m square minus omega square minus I gamma m omega. This I can write as 1 divided by m into omega m minus omega into omega m plus omega minus I gamma m omega. Right, so this is what I have. Now at resonance, as omega tends to omega m, at resonance I can write this expression chi m of omega at omega m. I can write it as m into this. I can nearly write it as omega is nearly equal to omega m, so let me write it as twice omega m, and it is not exactly equal to omega m, so let me retain this term. It is not 0. And then I have here I gamma m omega m, okay, and to the power minus 1. So this is what I have. So from here I can find out the modulus of chi m. Actually this is, as you can see, this is a Lorentzian, so you can see it more clearly if I take the modulus square of this function. That would be equal to 1 divided by 4 m square omega m square. You can do it yourself, it is easy to do. Omega minus omega m square plus gamma m by 2 whole square. Finally, let us work out this problem. Consider a Fabry-Pérot cavity with a two-level atom in it. The cavity is driven by an external laser with frequency omega L. An optical mode in the cavity is interacting with the atom in addition to its interaction with the bath or environment. Capture this situation by writing an approximate Hamiltonian. Okay, let us do it. This problem is akin to the James Cummings Hamiltonian. So we have this situation, we have this Fabry-Pérot cavity, and this cavity is driven by an external laser with frequency omega L, and we have an atom, two-level atom inside the cavity. So this one, it has energy En, the kth state Kt and Kz, and we have an optical mode inside it. Let me represent it by A cap. So this is in addition to this mode is interacting with the bath, and bath we can, as you know, that we can consider or model the bath as a collection of external harmonic oscillator. Each bath can be represented by an operator B I cap. Okay, ith oscillator, bath oscillator can be represented by this B I cap. Now let me write down the Hamiltonian term by term. First of all, let me consider this optical mode. This optical mode is a harmonic oscillator, so, and it has a frequency omega optical. So this is the energy of one energy of this whole mode would be h cross omega optical A dagger A. So this is the first part of the Hamiltonian, referring to the energy of the optical mode. Then the atom, we can model it as a two-level atom, as we have already seen. So this is h cross omega atom, we can write it as sigma z by 2. So this is the atom part of the Hamiltonian. And this atom field interaction I can write down as, so because of the this also you have already learned in the context of James Cummings model. So that would be h cross z, that is the interaction strength between the atom and the mode. So that would be A dagger sigma. Sigma is the atomic lowering operator. A sigma is the atomic A sigma dagger, that is the atomic raising operator. So this is what we have for the atom field interaction. Then this bath is also a harmonic oscillator. It's a collection of harmonic oscillator that I can write as H cross omega I bi dagger bi, right? And it is the cavity is driven by this external laser, so that we can capture it by writing it as H cross omega drive, that is the driving amplitude. And because of this drive, a photon is created inside this oscillator, inside this cavity. So we have a dagger e to the power minus I omega lt, so it has to be Hermitian, so we have this Hermitian conjugate is also there. Now we are left, the last thing is that there is a interaction between the bath and the mode, and that interaction we can capture by this particular term. So we have H cross, suppose this interaction between the bath and the optical mode is omega I, that's strained, and it's a complex quantity, so let us write it's a omega I star. This is A is the optical mode, and this interaction, because of this interaction, a optical mode may be annihilated and a bath mode may be generated inside the cavity. So all these things is captured by this particular Hamiltonian. So AI, it has to be Hermitian, so this part is the Hermitian conjugate part, right? So this is what we have. So this Hamiltonian captures the whole situation that is described in the problem. Only condition here is that this particular quantity bi bj dagger has to be equal to delta ij. Thank you.